Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research, from advanced biomedical technologies to breakthroughs in AI, material science, chemistry, and physics, all told as compelling, easy-to-follow stories. Today, we are looking at something that, well, it affects every single one of us, every day.
Oh, definitely.
So I want you to picture this. You're walking through your kitchen, minding your own business, and bam! You stub your toe on the leg of a chair.
Literally the absolute worst way to start a morning.
It really is. And think about what actually happens in that exact moment. You get that instant, sharp physical flinch, right?
Yeah, your foot jerks back, your eyes squeeze shut.
Exactly. And that physical event, it's over in a second. But then there's this lingering, grumpy, simmering mood that completely ruins the next, 5 minutes of your day.
Or more if it was a really bad hit.
Right. You're snapping at your partner, you're mad at the chair, you're upset. The physical sensation vanished instantly, but the feeling drags on. Which leads to a really strange question.
Go for it.
Why does a split-second physical sensation morph into a lingering emotional state?
It's one of the most fundamental questions about the human experience, really. And the answer has always been incredibly elusive.
But we have some news on that front, right?
We do. We're diving into some brand new research today where scientists have actually managed to capture the exact speed, the shape, and the literal echo of a feeling as it moves through the brain.
Wow.
Yeah, they haven't just tracked a mood, they found the physical blueprint of it.
I am so ready for this.
Yeah.
But before we get into how they pulled it off, we probably need to talk about why this has been such a massive mystery in the first place.
That's a good place to start.
Because when you look at the mammalian brain, whether it's, a human or a mouse, you're looking at this massive, highly distributed network. It's not like there's a dedicated, grumpy toe stub center glowing red in the back of your skull.
No, not at all.
Yeah.
The brain is entirely decentralized. You have millions of independent neural circuits scattered across all these different lobes.
Right.
So the core challenge for scientists was figuring out how these scattered circuits instantly communicate to turn a half-second annoyance into a unified, lasting bad mood.
Because there's a difference between a reflex and an emotion.
Exactly. We've always recognized that difference in practice. A reflex is binary and clean. If you touch a hot stove, your peripheral nervous system and your lower brainstem, they pull your hand back before you even consciously process the heat.
Right. It's purely about immediate survival.
Yep.
But the feeling of being upset that I burned myself or, the lingering fear of the stove, that's the emotion.
Precisely. And emotion is notoriously messy. It requires the whole brain to get involved. You need memory, context, a sense of self.
So it's complicated.
Very. Trying to track the exact millisecond of reflex officially becomes an emotion across a whole brain that was considered nearly impossible.
See, here's where it gets really interesting to me. Finding that transition point, it sounds like trying to figure out the exact microsecond a single falling raindrop officially becomes part of a puddle.
That is a great way to put it.
Yeah. But wait, couldn't they just put someone in an MRI machine, show them a sad movie or scare them and just, see what lights up?
That's a really common intuitive leap, but the technology actually works against us there.
Really? How so?
Well, an fMRI machine measures blood flow to different parts of the brain. And that's a process that takes several seconds to unfold. It's called the hemodynamic response.
Oh, okay.
But neurons fire in milliseconds. So by the time the fMRI shows us a lit-up area, the reflex is long gone, and the emotion is already settled in.
That makes sense. It's just too slow.
Way too slow. Plus, showing people sad pictures is incredibly subjective. You have participants sitting in this loud, clunky scanner, and they might be thinking about what they're having for lunch.
Or worrying about their parking meter.
Exactly. It's too muddy. So researchers needed a physical stimulus that was perfectly timed down to the millisecond.
Like a perfect controlled trigger.
Yes. It had to be safe, inherently annoying, and crucially, it had to evoke the exact same reflex and emotion in both humans and mice.
So they could actually compare apples to apples.
Exactly. So they could study the fundamental architecture of the mammalian brain.
Okay, so they needed the ultimate, universally annoying, perfectly timed trigger. What do they actually end up using?
They use the eye puff.
The eye puff. Wait, when you go to the optometrist for that awful glaucoma test and the machine just shoots a blast of air right into your eyeball.
That is the one. This brings us to a landmark study published in the journal Science in May 2025. It was led by Dr. Isaac Kavar, Carl Deisseroth, and a really large team at Stanford University.
Okay, so the Stanford team used the terrible eye machine.
They used a clinical device called a tonometer. and it delivers a highly precise 60-millisecond puff of air directly to the eye.
So it's fast.
Very fast. And it's entirely safe. No physical damage is done, but it is universally aversive. Every mammal hates it.
Oh, I hate it so much.
We all do.
Yeah.
So they administered this eye puff to both human volunteers and mice.
And just to clarify here, because this part is wild to me, they weren't just putting surface stickers on their heads to watch them blink, right? They were looking deep inside their brains.
Deep inside, the human participants were epilepsy patients who were temporarily staying in the hospital with deep brain IEG electrodes implanted for their medical treatment.
IEG, meaning intracranial electroencephalography, right? Like literally wires placed inside the skull directly touching the brain tissue.
That's correct. It's a rare and incredibly valuable opportunity in neuroscience.
I can imagine.
Because the wires are under the skull, they can record high-speed, localized electrical activity without all the interference of bone and scalp getting in the way.
Okay, that's the humans. What about the mice?
For the mice, the researchers use something even more advanced. They're called neuropixels.
Neuropixels. I've heard the term thrown around, but break that down for me. What are we actually looking at?
Think of a neuropixel as a microscopic silicon probe. It's much thinner than a human hair, but it's packed with hundreds of tiny recording sites.
Wow, okay.
So when it's inserted into the mouse's brain, it acts like a towering microphone array at a concert.
Oh, that's a cool visual.
Yeah, it allows scientists to listen to thousands of individual neurons firing simultaneously across different layers of the brain, all in real time.
Okay, so they have this unprecedented access in both humans and mice. They puff the air, it hits the eye for exactly 60 milliseconds. What is the actual reaction?
In both humans and mice, they observed a very distinct two-part physical reaction.
Okay.
First, there's a fast reflexive blink. That's the early phase. It's just your body's basic hardware protecting the eye.
Right, the flinch.
But then it's followed by a lingering effective squint. The eye stays partially closed and tense for a while after the air is completely gone.
A squint?
Yes, that lingering squint is the late phase, and it visually indicates a lasting negative emotional response. It's the physical manifestation of, I didn't like that, and I'm still bothered by it.
Okay, so we have a blink and a squint. I buy that the blink is a reflex, but couldn't the squint just be a slow muscle relaxing? Like, how do they definitively prove that a prolonged squint is actually a complex emotional state?
That is the exact right question. And to prove that the late phase squint was truly tied to an internal emotional state, they brought in a pharmacological twist.
Ooh, a twist.
They introduced a drug called ketamine.
Okay, let's unpack this. Because ketamine is an anesthetic, it numbs you. So I'm assuming when they puffed the air, the brain scans just went completely dark, right? Like the signal just stopped because the subjects were completely numbed out.
Actually, no. And that's what makes this so fascinating. In lower subanesthetic doses, ketamine doesn't act as a total blackout drug. It's a dissociative.
Okay.
Specifically, it's an NMDA receptor antagonist.
NMDA receptors, those are the chemical gates between neurons, right?
Yes, think of NMDA receptors like little molecular bouncers at a nightclub door.
Huh. Okay, bouncers.
They control how long the door stays open for electrical signals to pass between neurons.
Got it.
By blocking these receptors, ketamine doesn't stop the initial sensory signal from arriving at the club, but it closes the doors really quickly, stopping the signal from bouncing around inside.
So it shuts down the party early.
Exactly. The result is emotional blending. It disconnects your physical awareness from your emotional reaction. You still know things are happening, but the chemical pathway that assigns a bothered feeling to it, that is disrupted.
So what actually happened when the humans and mice on ketamine got puffed in the eye?
The results were stunning. The ketamine completely wiped out the lingering emotional squint. The face just immediately relaxed.
Wow.
But, and here's the crucial distinction, it left the fast, reflexive blink perfectly intact.
So the body still protected the eye?
Yes, the reflex worked perfectly, but the lingering bad mood just evaporated.
Whoa.
Well,
So they still physically felt a highly annoying sensation, but the chemical pathway telling the brain to be mad about it was just severed.
yes,
Did the human patients confirm this? Like, could they tell the researchers what they were feeling?
they did. Their verbal reports matched the physical data perfectly. During the baseline test, without the drug, they described the puffs as very unpleasant and visibly jumped.
Standard reaction.
But on ketamine, they reported that they absolutely still felt the physical puff of air. Their sensory awareness wasn't numbed at all, but it simply wasn't bothersome anymore.
That is so weird.
One patient even laughed and said the air puff felt entertaining.
Entertaining. Wait, really?
Yes, entertaining.
That is wild. The same blast of air goes from highly unpleasant to a fun little breeze just by altering how the brain's network communicates.
And because they were recording deep inside those brains with the IEEG wires and the neuropixels, they could actually watch this emotional severing happen at the neural level.
So what did the data look like?
When the iPuff hits, the brain's response happens in two distinct phases. Phase 1 is what they call the broadcast.
The broadcast. Walk me through that.
Within milliseconds of the air hitting the cornea, the sensory signal is blasted across almost the entire brain. It's a massive brain-wide alert saying, hey, incoming sensory data.
Okay, the alert goes out.
And surprisingly, ketamine didn't stop this broadcast at all. The data flashed across the network just like normal.
Which explains why they still felt it and blinked. The raw data arrived.
Exactly. But then comes phase 2. In a normal, unmedicated brain, that fast broadcast is followed by a persistent trace.
Trace.
Yeah, the signal settles into specific regions, primarily the orbitofrontal cortex, or ORB, and the insula, or INS. These areas are heavily involved in decision-making and emotional regulation.
Okay.
In those regions, the neural activity lingers. It reverberates. That lingering echo is the emotion.
So just bounces around in those two specific spots.
Yes. And when ketamine was introduced, blocking those NMDA receptors, that persistent trace was completely abolished.
Wow.
The broadcast happened, but the echo was silence.
Okay, I want to try an analogy here to make sure I'm wrapping my head around this.
Go for it.
It sounds like striking a massive brass bell in a quiet room.
Okay.
The reflex, the raw sensory data of the air hitting the eye, that's the physical hammer striking the metal. The whole bell feels the impact instantly. That's the brain-wide broadcast.
Right.
But the emotion, the mood, that's the lingering, vibrating ring that fills the room for the next 10 seconds.
Oh.
That's the persistent trace.
Yeah.
So did the ketamine basically act like a hand slapping onto the metal bell to instantly deaden the vibration?
That is a phenomenal way to visualize it. Yes, the ketamine acts as the dampener on the bell.
Awesome.
And to take that a step further, the Stanford researchers actually built a mathematical model to understand the exact mechanics of this dampening.
Oh, they did the math on it.
They did. They found that the brain's emotional state operates on a highly specific timeline. They defined a variable in their model called tau persist.
Tau persist.
Yeah, tau is the Greek letter often used in physics to represent a time constant. Here, it represents the brain's intrinsic timescale. Basically, the exact mathematical duration a signal is allowed to echo before it fades away into the background noise.
Tau persist. So it's the actual literal math of an echo.
Exactly. And what they discovered is that ketamine accelerates this intrinsic timescale. It speeds up the decay of the signal.
So it forces it to end sooner.
Yes, it forces the vibration of the bell to stop so fast that the emotion literally doesn't have the biological time it needs to take root.
That is profound. I mean, it means emotions aren't just located in a specific bucket in your head.
Right.
They aren't a place you can point to on an anatomical map. They are a rhythm. They're a whole brain network response that fundamentally relies on time. Like the signal has to ring for a very specific duration for you to actually experience it as an emotion.
It's a massive philosophical shift, really. For millennia, poets and philosophers have tried to define what an emotion is, and these researchers just reduced it to a measurable Greek letter for time.
That's incredible.
And it's a conserved evolutionary mechanism. We see the exact same time-scale-dependent dynamic in mice and humans, species separated by tens of millions of years of evolution.
So all mammalian brains do this?
Yes. The mammalian brain uses the duration of a signal to create the context of a feeling.
So what does this all mean? Let's zoom out a bit, because this isn't just about blowing air into people's eyes. If we understand that emotion is a mechanical timing issue, a persistence timescale, this has to have massive implications for medicine and psychiatry.
Oh, it completely reframes how we view human suffering and psychiatric conditions. If emotions require a specific tau persist duration to exist, we could start looking at mental health disorders not necessarily as chemical imbalances in a static location, but as disorders of timing.
Okay, let's play this out. What happens if the bell rings for too long?
We call that an overstabilized state. Let's take obsessive-compulsive disorder, or OCD, as an example. In a neurotypical brain, a distressing thought like, "Did I lock the front door?" is like a pull of air. It causes a quick broadcast, a short echo of anxiety, and then the bell stops ringing. You move on.
Right, you check it and let it go.
But in a brain with an elongated persistence timescale, that specific neural circuit won't decay. The echo of anxiety reverberates endlessly in a loop. The hand never stops the bell.
Oh, wow.
The same logic applies to severe, intractable depression, where the echo of a negative event persists far beyond its useful life. Or centralized chronic pain, where the brain continues to feel an injury long after the physical tissue is healed.
Wow. So the mechanics of suffering are just signals that refuse to fade.
Exactly.
But what about the opposite end of the spectrum, an understabilized state where the signal decays way too fast?
Well, if the time scale is too short, brain states can't stabilize long enough to form a cohesive context. The echo dies the millisecond the hammer
Yeah.
strikes. This closely mirrors the negative symptoms we see in conditions like schizophrenia.
Really? How so?
Specifically, it could explain the flattened affect, where a patient struggles to display emotional responses to significant events,
Hmm.
and also the disorganized thinking, because the neural network physically cannot hold on to a thought pattern long enough to string it together into a coherent sentence or narrative.
That makes so much sense. It's like trying to play a melody on a piano, but the key's instantly dead in the second you lift your finger. You just can't connect the notes.
That's a beautiful way to phrase it.
And what if it's just a chaotic environment? Where does something like autism spectrum disorder fit into this timing model?
In autism spectrum disorders, we often observe hyperexcitable neural networks. If those networks cause the local timescales and sensory regions to lengthen too much, you get a processing overload.
A processing overload.
Yeah, imagine trying to listen to a fast-paced conversation in a crowded room. Normally, your brain processes a word, lets it decay, and prepares for the next one. But if every single word, every background noise, and every shifting facial expression echoes loudly in your neural network for 10 seconds, the signals jam up. It creates a massive traffic jam of sensory information, making rapidly changing inputs incredibly overwhelming to process.
Building on that piano or bell analogy, if we know ketamine basically puts a hand on the bell to stop the ringing, could this research lead to highly targeted future therapies?
I think that's the ultimate goal.
Because I'm thinking of therapies that act more like a precision sustain pedal for our minds. Right now, a lot of psychiatric medications act like blunt force chemical sledgehammers that just numb everything.
Yeah, they do.
Could we eventually learn to gently tune the specific duration of our feelings?
That is exactly the frontier this research opens up. By isolating this tau persist variable, and by mapping the exact circuits in the orbitofrontal cortex and insula that hold these echoes, we are moving away from the sledgehammer approach.
Which is huge.
Massive. The future of psychiatry could involve interventions, whether that's highly specific next-generation pharmaceuticals or targeted deep brain neurostimulation that act as that precision-sustained pedal.
So you wouldn't just be numbed out.
No, the goal wouldn't be to erase a patient's ability to feel sadness or anxiety. You would just tune the decay rate so a fleeting moment of panic doesn't stretch into a whole day of paralysis.
That is incredibly hopeful. It frames mental health not as a broken machine that needs its parts replaced, but as an instrument that just needs precise tuning.
It's a much more empowering way to look at the brain, for sure.
Let's summarize the key takeaways from this Stanford data, because we've covered a lot of really complex ground today.
Let's do it. First, we now know definitively that emotions happen in two measurable steps. There is an incredibly fast brain-wide data broadcast, followed by a persistent, localized echo in specific regions like the insula that actually generates the subjective feeling.
The hammer and the ring.
Exactly. Second, science has proven we can chemically separate physical awareness from emotional suffering.
Right, the bouncers at the door.
Yep. By manipulating NMDA receptors with ketamine, researchers showed that you can remain fully conscious of a negative physical sensation without having to suffer the lingering emotional consequences of it.
The entertaining eye puff. The raw data arrives, but the bad mood is canceled.
And third, the overall health of our minds is deeply mechanically tied to the time scale, the literal millisecond duration of our neural networks.
It all comes down to time. Our feelings, everything we love, everything we fear, every grudge we hold, and every moment of joy we experience, it's all ultimately a matter of timing.
It really is.
The physical world happens to us in a flash, but our entire reality, our actual lived experience, is built entirely in the echo.
We are the lingering resonance of our experiences.
Which leaves us with a pretty wild thought to mull over. If our deepest emotions, our most profound traumas, and our greatest joys are just a matter of how long a signal echoes in the physical wetware of our brain, what happens if we eventually unlock the ability to manually tune our own emotional sustain pedal?
It's a huge question.
If you could perfectly control how long you felt sadness or how long a moment of happiness echoed in your mind, What kind of emotional reality would you choose to live in? It's something to think about the next time you stub your toe. Thank you for joining us here at Deep Dive Lab. If you loved uncovering this mystery with us, please follow and subscribe for more fascinating science stories unfolding in real time. We'll catch you on the next deep dive.